All right, for our next talk, I want to introduce Duncan, who is a senior applications engineer at Imperas software, and the talk is called Hybrid Simulation with Emulation for RISC-V Software Bring Up and Hardware Software Co-Verification. Please go ahead.
Thank you. Good afternoon, everyone. A bit of a mouthful. What I want to do is give you some background, talk about what we need in place in order to allow us to do hybrid simulation, and the use of it in the bring up of software, the verification of software with hardware, and emulation of the hardware. So a little bit of background. So looking at the Imperas timeline, we started creating models of RISC-V about 6 years ago. So we've been providing models of other architectures before that, but 6 years ago we decided to join the RISC-V Foundation and start creating these models. About a year after that, so 5 years ago, we had our first customer, our first paying customer, that was using those models, the software development tools, and also the design verification, or using them in a design verification methodology. About a year after that, they taped out and had a successful SoC developed. Skipping forward, we announced earlier this year a relationship, an OEM with Cadence, so that Cadence can actually now resell the Imperas models as part of their development. So this talk is actually based on a talk that was given at CDN Live earlier on in this year, and sort of a cut-down version, hoping to get the salient points without too much of the other stuff. So why? So who's using it, and why are they using it? So the who's the usual. It's probably a lot of the people in the audience here today. It's the usual semiconductor companies, but it's also now embedded systems companies who are looking to migrate up in the market, so do their own development of their own SoCs. We know what RISC-V architecture is, but just to say it again, it's an instruction set. It's not a processor implementation. So everybody is having to create, using that ISA, their own implementation of the RISC-V processor. Now, where are we seeing it? Well, we're seeing it in places where the x86 and the ARM are not prevalent. So we're seeing it in the small microcontrollers, so replacing proprietary cores. We're seeing people using it in verticals, such as IoT and automotive. We're seeing it across in other areas, things like security, AI, ML, and then also in deeply embedded applications. Some data we got is that RISC-V processors are now used in over 30% of all SoCs. It might be a small core in a corner doing some management, some upkeep. It might be an actual application processor. Well, what's happening is the freedom of the ISA, as we all know, is actually allowing people to develop differentiated products and domain-specific processing systems. So how are we going to be successful? As we know, RISC-V is very complex. It's very configurable. We have many functional groups of instructions that we can use and choose to use. We have things such as the atomics, floating point, the vector units that can all be used and configured within the base processor. And then we can add the things such as the interrupts, exception unit, privilege modes, debug modes. We can have multi-heart processing. And so this starts becoming complex. Now, this complexity adds stuff we need to do additional for DV, makes it more complex. It means we have to develop more complex tool chains to take into account automatically all these new features and the specific features. So we need special ways, or we need improved ways of developing the hardware, verifying the hardware, and developing the software. So processing subsystems, here we're just showing three processors or people developing processing subsystems that we're aware of and we're being used with. We have Dolphin Designs, who are doing a multi-core DSP-based processor on RISC-V. We have Meta, who are doing an 8x8 matrix training engine, an inference accelerator. And then NSI Texi, which is a data flow processor. So it's been used in various different ways, from having common multiple processors to very different processors within one SoC. So currently, to verify our processor RTL, we need to run on RTL simulations. We also need some form of step and compare to be able to check that the execution of RTL matches the specification. And we need to have verification IP and also functional coverage to make sure that we're actually executing and testing everything that we think we are. In terms of software development, then we've got the possibility of using virtual platforms. We can use FPGA prototypes, and we can do work just based on host machines. So these are conventional ways, but we don't think they're adequate to do everything this day and age. We think there's actually a need for the hardware emulation, for software virtualization, and for the hybrid approach using the software virtual platform and hardware emulation. So just to give you an idea of what a hybrid would look like, what you have is you have a virtual platform, so a software simulated element, and then you have on the FPGA-based or hardware accelerator the RTL executing. One of the key elements, and the reason we're talking today, is the processor modeling. So we think there's a number of requirements for a good RISC-V processor model. So we think that you need to have something that represents all of the ratified specs, plus also unratified specs that are stable. As well as that, you need to support all the different versions available. So if customer X starts building their SoC at version 0.8 of a specification, then that's the version they want to be able to test against. They don't want to have to go and maintain their own model when the version moves on and other models move on. You want to be able to include other elements, so interrupt controllers, so other behavioral components. It needs to be user extendable. So as we know with RISC-V, one of the key advantages is the flexibility, the freedom to add new instructions and to change it. So you need to be able to add your own instructions. You need to add your own new custom register files. You also want to be able to model actual IP. So many vendors exhibiting here have got their own IP. You want to actually be able to select that particular IP. You don't have to go and manually change things yourself. So the likes of Andes and Sci-Fi, Codasip, MIPS, Open Hardware, then you need to actually be able to select and use their particular IP in your model. And on top of that, you need to have well-defined test processes. You need to have coverage metrics, so you know that everything's been covered. And we think we need to have mutation testing, so you're actually changing your test algorithm to make sure that everything is being covered and that everything is being made visible. And then finally, you need some interfaces. So you need interfaces so you can use this model in System Verilog, System C, the Imperas virtual platform environment. You now have ability to use debug tools, attached debug tools, standard GDBs, Eclipses, Imperas MPD, multiprocessor debug environment here. And then software analysis tools to allow you to actually access the internal state of your processor and see exactly what's happening at any one time. And then finally, you need to be able to do exploration and add potentially other timing estimation and get other levels of accuracy. So we think most RISC-V ISSs will provide at least 2 or 3 of these, but possibly not all. We've actually been developing processor models for over 15 years. We started with ARM and MIPS, Renesas, and other cores. So building on that expertise and that understanding, we actually started from then designing processor models and the simulator to provide all of these requirements. As we thought of them all as being essential to give a model that can be used in and for verification. So the model itself is built up of various parts. You see on the leftmost block the base model. So this is the base model that will provide you with all of the extensions, as I said, all the different versions of the extensions. This is pre-compiled and verified, so that when you use that model, you know that it's a good model. In the middle, you can see we have ability to configure that model. So this configuration could be selecting specific IP vendors' processors. It could be tweaking the actual way in which certain aspects of the RISC-V specification work. We've seen from various vendors that we work with that everyone can have a slightly different interpretation of some of the areas of the specification. So you need to be able to accommodate that in your base RISC-V model. And then you need to be able to, the user needs to be able to extend the model themselves. So we need to provide a good set of APIs allowing a clear way of extending that model without making any difference to the base model. And then we use that model in two places. We can use it in the processor DV flow. So we can use this to verify our RTL is doing what we expect it to do based on a sequence of instruction executions. But we can also use that in a software simulation environment. So we can use exactly the same model both for our software development and for our RTL verification. Models can also be used to actually drive the customization. So here we see a loop. So we start with a base RISC-V model, RISC-V processor. We use analysis tools to look at how our algorithm or our application is executing on that RISC-V processor. Based on that, we can analyze and generate different customized instructions, targeting our particular algorithm. And then we can go and possibly hand edit our application to add intrinsics or add assembler for the, or even just the data binary for the new custom instructions, and then re-execute that, reanalyze it. And by going around this loop, we can actually start characterizing our application and seeing what type of customizations are really appropriate and give us the best advantages. Of course, when you add custom instructions and other customizations, you actually still want to be able to use all your tools. So you want to be able to see any new custom state registers or register file registers that you add. You want to be able to see your instruction execution in your debugger or your trace tools. But also what you want is those models to be portable into your other environments. So here we show the models being picked from a library within the Cadence hybrid Helium platform. So those are selected, the interface is selected, and they're instanced into a hybrid simulation platform. Again, when you move into the hybrid world, or the third-party tools, you still want to be able to see all of those new customizations that you've made. So as well as all the internal state of your base RISC-V processor, you can see all the new state, new custom instructions that have been added to that processor. So let's talk a little bit more about the actual virtual and hybrid platforms. And again, this is tailored towards the Cadence, Helium, the Palladium, and the FPGA Protium boards, but this is applicable to any vendor. So why hybrid emulation? So actually, hardware emulation is very valuable to allow you to run your RTL and do software co-verification. So it allows you to do low-level development and do porting and bring up. Unfortunately, hardware emulation is very expensive, and so therefore it's typically a very scarce resource. Not in so much as it's not available, it's just very, very heavily used. It also turns out to be a bit slower than real time. Although it's faster than RTL simulation, it's still slower than real time. So what happens when we have an event that's after we've executed a billion instructions, that is what we actually want to be able to analyze. We don't want to have to run we don't want to have to run the emulation for hours and hours before we get to that point. So this is why we need hybrid. So we have the speed of the software simulation environment to get us to the point of interest, and then we have the accuracy of the hardware emulation on the RTL to actually use the true RTL and verify it against the software drivers against it. We had an example working with the RISC-V processor where they were actually booting a Linux kernel and then wanting to test drivers. The Linux kernel booted for about 22 hours before they then found a bug. So we don't want to be there. This is where we want hybrid. We want to be able to run that 22 hours in a much, much shorter time, half an hour possibly, even shorter, before we then run the actual drivers themselves. So in terms of the Helium Palladium, what we actually created was a virtual platform. It used a RISC-V model from Imperas and also the platform level interrupt controller model from Imperas. These were interfaced into the Helium virtual platform, also using other System C TLM components. The connectivity between the virtual platform and the Palladium was via an AXI bridge. So we're now able to execute both the fast elements and also the accurate RTL on the Palladium, on the hardware. So looking at an actual joint customer, so what I've talked about is real. We have this all working. A joint customer we have in place is an SoC that's targeting AI and machine learning. It's got over 140 cores. These are actually based on the Andes RISC-V cores. It's a mix of scalar and vector processors. The processors themselves are used for the AI ML, but they're also used for firmware and for low-level SoC functions, such as the power management and chip communications. The total platform simulation runs at over 500 million instructions per second in simulation, and the users can choose whether they're going to run the whole firmware stacks, they're going to run particular drivers, or essentially run the bit that's of interest to them. They actually got the software up and running a year before the RTL tape-out. Once they got the RTL back, they had it running within days on that SoC. So this is a key thing here. We want to make sure we've got in a position where we get everything in place, so when we have got our SoC back, we're already pretty much up and running and fully tested. So to finalize, we think hybrid is a simulation emulation is really important in the verification, software bring up, hardware software co-simulation. We think that it requires an accurate processor model that can be used in different environments. And the same processor models should be used in both the processor and the SoC verification environments, and also for the software development, debug, and test. Thank you.
Okay, thank you. Any questions? All right, so one more round of applause.
Thank you.